Hello, everyone. Welcome to our session on computer science for Class XI. Today, we'll be exploring the fundamentals of computer science, starting with an overview of what this exciting subject entails. We'll cover key concepts, important topics, and give you a glimpse of what you can expect to learn throughout the course. I'm thrilled to have you here and look forward to an engaging and informative presentation. Let's get started. Welcome to Unit II. In this section, we're going to dive into some foundational concepts that are crucial for understanding the broader topic. We'll explore the key points thoroughly, but in a way that's easy to follow and engaging. The goal here is to highlight the most important ideas so they really stand out. As we go through, I'll connect these points back to the overall theme of the presentation, showing how they fit into the bigger picture. This will help you see not just the details, but also how everything interrelates and builds on what we've covered earlier. So, let's get started and explore these core concepts together. Computational thinking, or CT, is essentially a problem-solving process. It's about breaking down complex problems into manageable parts and developing strategies to solve them. Computers can be incredibly helpful tools in this process, acting as assistants or even partners in solving these challenges. But before we can effectively use computers, we need to understand how problems can be solved, what steps or methods are involved. That's where computational thinking really shines. It helps us see the problem-solving process clearly, so we can apply it not just with computers, but in many areas of life. Throughout this presentation, we'll explore how computational thinking connects with programming and how it can enhance our problem-solving skills overall. Now, let's take a closer look at some key techniques that can help us think computationally when faced with a complex problem. First, looking for similarities among and within problems is really important. It helps us recognize patterns and commonalities that can guide us toward solutions. Next, focusing on the important information means we filter out irrelevant details and concentrate on what truly matters. This keeps us efficient and clear-headed. Then, breaking down a complex problem or system into smaller, more manageable parts makes the whole process less overwhelming. It's like solving a big puzzle step by step. These techniques are essential because they help us think logically and systematically before we even start writing code. They form the foundation of computational thinking, which is all about approaching problems in a structured, strategic way. Let's start by looking at the type of output variable required, which we call the problem definition. This is essentially what we want the solution to produce. Similarly, we need to identify the type of input variable required. These are the data or information the problem needs to function. Understanding the data requirements of the problem is also crucial. It helps us figure out what kind of data we need to gather or analyze to solve the problem effectively. Now, the process of understanding and then defining the problem is really the foundation of any problem-solving approach. In almost every methodology, the very first step is to clearly define or identify the problem itself. This step is actually the most challenging and important because it involves diagnosing the situation thoroughly. The goal here is to focus on the real problem, not just its symptoms. This means looking beyond surface issues and getting to the core of what's really causing the challenge. When we analyze or define the problem, we're setting the stage for the entire problem-solving cycle. Remember, this step shapes how we approach solutions later on. It's about being precise and clear so that subsequent steps are effective and targeted. So, in summary, understanding the problem and defining it properly is the key to successful problem-solving. It's the step that guides the entire process and helps us avoid wasting effort on symptoms rather than the root causes. Let's take a closer look at some of the key tools we use in designing software solutions. On the slide, you see pseudocode, flowchart, and algorithm. These are essential because they help us plan and organize our ideas before jumping into coding. Pseudocode is a way to write out the logic of a program in plain language that's close to programming syntax, but easy to understand. It helps us visualize the steps without worrying about syntax details. Flowcharts give us a visual representation of the process, showing the flow from one step to another with symbols and arrows, making complex logic easier to follow. Algorithms are step-by-step procedures that solve specific problems. They're like detailed recipes for your program. All of these tools support the overall design process, which is about transforming user requirements into a workable plan. This planning phase is crucial because it guides the actual coding and implementation. Remember, the design process is part of the broader problem-solving cycle, where we analyze, plan, and then develop solutions efficiently. So, by using these tools, pseudocode, flowcharts, and algorithms, we make the design more structured, clear, and manageable. This ultimately helps us build better, more reliable software. Now moving on to step 4. Here, we compare the two numbers, and if A is greater than B, we display A is the largest number. Otherwise, if that condition isn't true, we display B as the largest number. This step is crucial because it helps us determine which number is bigger based on the comparison. Remember, this is the decision-making part of our algorithm, where we evaluate the condition and then act accordingly. It's a simple yet powerful example of how algorithms process information to produce a result. So, a flowchart is really just a visual way to represent steps in a process. It helps us see the sequence of actions clearly. Think of it as a map that guides us through a series of steps, whether we're looking at an algorithm, a workflow, or any process. Most flowcharts use boxes of different shapes to represent different types of steps, like starting points, decisions, or actions. And these boxes are connected with arrows, which show the flow from one step to the next. This makes complex processes much easier to understand at a glance. It's a powerful tool for communication, especially when you want to illustrate how different parts of a process fit together in sequence. Remember, the key points are that flowcharts are graphical, show steps in order, and use boxes and arrows to connect those steps. They're really useful for visualizing and explaining processes clearly and efficiently. Let's take a closer look at flowcharts and how they visually represent processes. The lines on a flowchart show the flow or sequence of steps, guiding us through the process in the correct order. When you see a rectangle, that indicates a specific operation or action that needs to be performed. A diamond, on the other hand, is a decision point where a choice must be made, leading to different branches in the process. Now, a circle or an oval, which we call a terminator symbol, marks the start or end of the entire process. It's like the beginning or final point of our workflow. It's also important to understand that different shapes have standard meanings in flowcharts, helping us quickly interpret the diagram. For example, a document symbol represents information entering or leaving the system. Think of it as the input or output of data. By understanding these symbols and their meanings, we can better analyze and communicate complex processes clearly and efficiently. This visual language makes it easier to see how each part of the system connects and how decisions influence the overall flow. Let's take a closer look at some key components of pseudocode. First, we have if, then, else. This is a decision or selection structure where you make a choice based on a condition. Any instructions inside this selection or iteration are usually indented to show they belong to that block. Next is FOR, which represents a counting loop or iteration. It's used when you want to repeat a set of instructions a specific number of times. Then there's output or write, which simply indicates that some information will be displayed on the screen. Moving on, repeat, until is a loop that continues executing until a certain condition becomes true. The condition is checked at the end of the loop, so it guarantees at least one execution. Similarly, the WHILE loop checks its condition at the beginning, so the loop only runs if the condition is true from the start. Finally, input or read indicates that the program will accept input from the user. It's important to remember that pseudocode isn't a programming language itself. It's a simple way to describe instructions clearly without worrying about strict syntax rules. While there aren't universal standards, these common structures help us communicate algorithms effectively. Let's take a moment to clarify the difference between an algorithm and pseudocode. An algorithm is essentially a well-defined sequence of steps designed to solve a specific problem. Think of it as a clear recipe that guides you through the process. Pseudocode, on the other hand, is a way to represent that algorithm. It's a method that uses a format similar to high-level programming languages, but without the strict syntax. While you can describe algorithms in natural language, pseudocode provides a more structured and clear way to outline the logic. One of its key advantages is that it doesn't rely on any particular programming language syntax, which makes it easier for programmers familiar with different languages to understand and interpret. Another important point is that transforming an algorithm from pseudocode into actual programming code is generally much easier than doing so from a natural language description. Pseudocode acts as a bridge, simplifying the transition from the logical steps to the real code you write in a specific programming language. So, in summary, the algorithm is the blueprint, and pseudocode is a practical way to represent that blueprint in a format that's both understandable and adaptable across various programming contexts. Implementation refers to the process of adopting and integrating a software application into a real environment. When we talk about implementation, we're essentially discussing how a new tool or software is brought into everyday use within an organization. This step is crucial because it's where the theoretical benefits of new technology are put into practice. The implementation process can sometimes be quite complex, especially for larger organizations or when the software itself is sophisticated. There are many factors to consider, like ensuring the software fits into existing systems, training staff, and managing change effectively. It's important to recognize that successful implementation isn't just about installing software. It's about making sure it works smoothly within the organization's workflow. This aligns with our overall theme of effective technology adoption. It's not enough to just have the right tools. We need to integrate them thoughtfully to realize their full potential.